All right, ladies and gentlemen, class recording has started. So, on Friday, we started talking about motion graphs. First, we said that graphs are a good way for us to look at relationships, right? Relationships between variables. On Friday, we introduced the idea of a position versus time graph. So like it says up on the board, position versus time graphs answer two questions for us, right? What two questions do those position versus time graphs answer for us? Where and when, okay? Position tells us where, time tells us when, okay? We said that a position versus time graph can also tell us a third thing as well. Even though it's not directly stated on the graph, what else can we figure out from a position versus time graph? The velocities from what, Ronnie? What tells us the velocity on the position versus time graph? The slope of the line will tell us the velocity. So, we started going through a couple of graphs and talking about what they told us. This is the first graph that we looked at, right? Well, actually, this is the first graph that we looked at, right? And we looked at these two swimmers, and we talked about where they were in displacement and all those fun things. But we also talked about how we could tell that swimmer 1 was faster than swimmer 2. 1, because she went a farther distance in the same amount of time, but also 2, because this slope of her graph is steeper than swimmer 2's graph. Okay? All right. Then we started looking at some other graphs. So first, the pink section on this graph, what did we say was happening there? At rest, right? What's the slope of a horizontal line? 0. And so pink lines, horizontal lines, represent no velocity or 0 velocity. Okay? Then we took a look at this graph here, and we compared green versus blue. What's true about green versus blue? The green section versus the blue section on this graph. They're both constant velocity, but what? One's steeper than the other one, so that means what? One's going faster than the other one. Which one's going faster, green or blue? Green. Okay? So steeper slopes mean faster speeds, slower slopes mean slower speeds, or lower slopes mean slower speeds. Right? Then we introduced this section, right, with the negative slope. And what's true about the negative slope? That means what? It's going opposite direction, right? Something is going to turn around and go in the opposite direction than what it was originally going or whatever, right? And then we talked about this graph, right? And we talked about specifically the green section versus the orange section. And what did we say was true about the green section versus the orange section? Same speed, but different directions, so that means they would have a different velocity, right? Same idea, just make sure that got that vocab. Okay? All right, good with those. Okay, now let's go. Where are we here? Okay, let's go here. Okay? Hopefully, a graph that looks familiar to you. Okay? This is the graph of what the marble rolling down the hill should have looked like from your lab that you turned in today. Okay? So, what's different about this graph versus the previous graphs that we've looked at? It's not constant, right? It's not a straight line. It's a curved line. Okay? Say again? It does have 4 dots, yes. Okay? So, in fact, we learned while you guys were doing the lab on Thursday of last week, right, that specifically what shape is this, Jafar? It's a parabola. Technically, it's half of a parabola, but it's parabolic, right? So, but more importantly, what is happening to the slope of this graph? It is increasing, right? It starts off, all right, so this graph starts off with a shallow slope. There it is. Right? But then as we go along, the slope of that graph keeps increasing, 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 increasing. What is that telling you about the object? It's getting faster. Because the slope tells us the velocity. So if the slope keeps increasing, that means the velocity keeps increasing, right? I'll throw a term out there now. If you don't understand that term, don't worry about it. Are we familiar with the concept of a tangent line? Those of you in geometry probably should be, right? Okay. A tangent line is something that hits the curve in one spot and one spot only. Okay? It intersects the curve in one spot and one spot only. So here, technically when I take this meter stick and I go like this, I'm showing you the tangent line to that parabola. Right? If you don't understand that, don't worry about it. But if you should, you do understand that the slope of this graph keeps going up. Okay? Because curved lines on position versus time graphs indicate changing velocities. This is the first one on the back. So anytime we have a curved line on a position versus time graph, that indicates that the velocity is changing. Like we said, here, right, what is this indicating about the object here? If we saw this object, what would we see it doing? How would we describe it if we saw this object out there? Well, rolling down the hill, because what's happening to it as it's rolling down the hill? It's speeding up. It's getting faster. It could also be something that is like a car that is going faster and faster and faster and faster. Any object that is speeding up would look like this, basically, right? Okay. All right, let's take a look at this one. What's happening here? Discuss with the person next to you. What's happening in this graph? Go.
Going up. So like when it's going really fast, it peaks and starts going backwards. Look, it looks like that's not very like dramatic, but it looks like it's going down. You gotta tell me I'm wrong. It looks like it's going up.
I'll give you that. All right, let's discuss. Jules, what's happening in this graph? You were? Okay, it starts off going very, very fast, but it slows down. And eventually what happens to this object? It stops. Because at the beginning, this has a really, really, really steep slope, right? But then as it goes along, that slope gradually and gradually and gradually decreases until eventually, what do we see about the slope of that line, or this graph? It's horizontal. It's a horizontal line. We have a zero slope. That means it eventually stops. Okay? Good there. All right. Here's what I want you to do. In the space maybe like right above those graphs, or right below those graphs, or whatever, okay, I want you to draw an XY axis. Now you can draw an XY axis, like you can basically draw the first quadrant of the XY axis, if that helps. Just like above those two graphs might be a good place to do it, because it relates to those two graphs. All right. So x-axis time, x-axis time, y-axis position. Okay. I would like you, and the person next to you, if you would like, or you can do it by yourself. I want you guys to draw me a position versus time graph for this motion. Ready? Ready? So just for somebody who's watching on the recording, I threw the ball straight up and caught it right back where I threw it from. Okay? So draw me a position versus time graph. for this motion?
Is that right?
Dude, you only do it once.
I want you to draw it.
Is that right?
Throw it up, it stops it rolling, it starts going faster, and then it starts slowing down at the
Yes.
top, then goes back
Although
down.
the right-hand side of your parabola seems like it goes back in.
You only do it once.
Yeah, it comes down with more force because of gravity acting on it as along with the ball goes back this way. But my graph is
Look at that.
but my graph is you can tell that it looks a little tilted. So in theory, it's not. It is just going up and then down. That's just my bad drawing on my graph part. The parabola is correct. What?
All right.
Perfect.
Told you. So
Did it, see?
this is what
It doesn't start like that.
that graph should look like. Okay? So, first, displacement. Remember, let's go through our vocabulary. Okay? What is the displacement of this motion? 0. It starts right back, or it ends right back where it starts, as long as I catch it at the same spot. Okay? If we go on this graph here, right, on the y-axis, it starts here. It goes away from the or x-axis, but then it comes right back and ends up right back where it started, at least on the y-axis. Does that make sense? All right, so that's displacement 0. Okay? Next, what happens to this ball? Oh, sorry, go ahead. That's what its displacement would be, right? Hold on to that question for a second, Jules. All right, so next, what happens to this ball on the way up? Before it stops, what does it have to do? It's got to slow down before it stops, right? When it leaves my hand, think about energy-wise, right? What happens to the kinetic energy on the way up? It decreases because the ball is slowing down. Here, right, during this section of the graph, what's happening to the slope of that graph?
Going up. It's getting wider.
It's decreasing, right? It's becoming shallower and shallower and shallower and shallower, right? What happens to the velocity of the ball on the way down? What happens to the velocity of the ball? It increases, right? But what's different about the slopes during the green section versus the slopes in the red section or pink section? Negative, positive. So when it gets to here, right, way down on the far right side, this has a very steep slope. It just is pointing which way? It's a negative slope, right? Negative only tells us what direction, not which way. How fast is the ball going right before it gets back to my hand? Pretty fast. It's just going fast which way? When it gets back to my hand, it's going negative, right? It depends on how fast I throw it up. Just how fast it's back, okay? Does that make sense? Question. What happens to the ball at the very, very top? It has to stop, right? Let's think about it from this standpoint. All of the slopes during the pink section are positive. All the slopes in the green are negative. But to go from being positive to negative, what do you got to pass through? You got to pass through 0, right? So up at the very, very top, when it hits the top of the motion, at the boundary between orange and green, or pink and green, What is the velocity, or what is the slope of the graph at that very point? 0. Has to be. Okay? Does that make sense? Okay? So, Jules, to answer your question or to answer your next question, right? You're asking about this situation, right? Ready? Okay.
Keep going.
Displacement would be different. So what happens to this graph if I let the ball fall all the way to the floor? It goes negative, meaning that what was the reference point in my graph?
Your hand.
My hand was the reference point, right?
It goes negative based on where you threw it from.
Based on the reference point, my hand.
That's just hiding from the floor.
Yeah, if I threw it from the floor, then, or if I did this, let's say this, right?
Then it'd be higher up
Right?
than the reference
That would
point.
start, that would be,
The pen. Pen.
that would look like this. And then technically it would go like this, because it stays there.
No, I was talking about something more like this.
All right. Good? What kind of displacement is it? It's displacement is a vector quantity, right? So here, on the red graph, if it ends up lower than where it started, it's a displacement in which direction, positive or negative? Negative. So it ends up a meter below where it started. But in this case, in the blue, it started at 0 but ended up at some positive number, so it ends up a meter up from where it started. Does that make sense? All right, good with that. Okay, let's transition and let's talk about this graph. Okay? So, what's the difference? Well, actually, let me answer this question. What's happening in this graph? Talk to the person next to you. What's happening in this graph?
Something is traveling at a constant speed. Constant speed. Constant velocity. Constant something. It's traveling.
All right, so in order to answer the question of what's going on in this graph, you need to look at the graph, right? And you need to notice that this graph is different from the other graphs we've looked at so far. What's the one difference in this graph versus the previous graphs? What's on the y-axis? Speed, right? So, in this case here, the speed is gradually increasing. What's happening to that object? If we saw it, what would we say is happening to it? It's going faster, right? Accelerating is a tricky word. Let's not use that one just yet. So, another type of graph we look at is a velocity versus time graph, right? So, velocity versus time graphs tell us the instantaneous velocity of an object over a specified period of time. Okay? Before we go any further, let's discuss this word, instantaneous. Okay? I'm assuming most of you are probably not familiar with that word. Okay?
Instantly.
But it does have what other word in it? It has instant in it. Okay? When we talk about instantaneous, it's an adjective that tells you right now or at one specific moment in time. Okay? Or what's happening instantly. Okay? So when we talk about the instantaneous velocity, we talk about what is the velocity of the object at any particular moment in time. So at 1 second, the instantaneous velocity is 4 meters per second, because that's what the velocity was exactly at 1 second. At 2 seconds, the instantaneous velocity is 8 meters per second, because that's how fast it was going at that particular moment. Okay? Does that make sense as far as instantaneous goes? Okay. What? Particular? So, when we talk about the instantaneous velocity, we said that velocity tells us what? So a graph of velocity versus time tells us what is the object doing at any particular moment in time. When and what. Okay? Does that make sense? So it's not where, what. So, let's take a look at this graph, which you guys have on your sheet. Talk to the person next to you. What's happening in this graph here? Go.
It's decelerating.
Going at a constant pace. A car is
Is it red or red? Oh. There's a red light and it's stopping for the red light.
going 5.
That's their purple is their green.
Alright. So, a shape that is similar to a graph that we've looked at previously. But because this graph is labeled something differently, it tells us something different. So what's happening during the yellow section of this graph? It is moving with a constant speed. Okay? Cruise control. All right? But then, what happens during the pink section? It slows down. Those values for speed keep getting closer and closer and closer to what? 0. So now on this graph, on a speed graph, where does the graph have to be for an object to be at rest? Or where does the graph have to be? It's got to be on the x-axis. That's the only place that shows rest on this graph. Okay? Good there. Okay. Now we're going to make a jump. All right? This is harder than what we've done so far. Okay? So if you don't get it the first time, just stick with it. We'll talk about it. All right. Here's a graph. Okay? This graph is actually a little bit different than the two graphs that we've looked at already. Okay? I'm going to highlight a couple of different sections on this graph. Correct. Okay. I've labeled all these different sections different colors for a reason. Here's what I want you to do. Before you even start answering the questions that are next to it, okay, I would like you to discuss with the person next to you what's happening in all the different colored sections of this graph. No pencils, no pens, no writing anything down. Just describe what's happening to the object during those different sections. Discuss. Go.
Red at rest.
No, green is increasing. Yellow is constant. Purple is decreasing.
Great, so
What about that one?
does that mean it's going backwards? It's going down.
And then the
It goes up. I don't think it's working.
You were on a roller coaster.
So what's the velocity? Velocity is like,
how fast they come in meters it's going in.
is that how fast and in what direction?
Wait, no.
30 seconds, and we'll discuss as a group.
Is velocity which direction? How fast and in which direction? So, okay,
Yeah, Jules.
you pass this house. This guy doesn't just like that.
All right, let's discuss.
This person's confused.
So, first, this graph is a little bit different than the two previous graphs we've looked at, in that what is the y-axis labeled as here? Velocity. Whereas the previous two were just labeled as what? Speed. Well, we did position earlier, but okay. Jules, what's the difference between speed and velocity? You can give me one word. Direction, right? Speed doesn't tell us which way something is going, but velocity does. And how do we distinguish one direction from the other direction?
Up and down.
Positive and negative. Well, up and down, we have to distinguish as positive and negative on a graph.
But if it's not negative.
Positive, negative. So, what does red represent on this graph? At rest, because those are what velocity? Zero velocity. So, if you look at the 6 questions directly to the right of this graph on your outline or on your sheet, you'll see that the first question is, when is the object at rest? So let's just kind of go general, right? So we'd say, I don't know, between 0 seconds and 50 seconds maybe? No, sorry, 25, because each of those hash marks is 50. And then, generally speaking, I don't know, between 200 and 275-ish seconds. Does that make sense? Yes, Javar, or no? Is that a yes, or is that a...
I would say 2.
Oh. Okay.
What goes here?
Velocity. We just talked about that, right? So velocity has to tell us what two things, right? Okay, so Sartosh brings up something good here. On your outline, underneath where it says velocity versus time graphs, right? It says a graph of the instantaneous velocity over a specified period of time. But, like we just discussed, velocity is different in speed in that it has to tell us two things, right? So the magnitude of velocity tells us what? How much, or in the case of velocity, that how much would describe how fast, right? So velocity, magnitude describes us how fast, or we could also call that what? Speed, but it also has to tell us the direction, or which way is it going. So it also has speed, but also which way. All right, good there. Okay, what does yellow represent on this graph? Constant velocity. So question number 2, when is the object traveling forwards with a constant velocity? So the yellow section is between, I don't know, 50 and 125? I mean, I won't be real picky about the numbers, but, you know.
Right there.
So, let's jump down.
It starts at 50. What is the object?
Let's jump down to question number 4. Right? Question number 4. When is the object traveling backwards with a constant velocity?
Like 290. Close to it.
What do constant velocities look like? Not just straight lines. More descriptive than that. Horizontal lines are constant velocity. Are there any horizontal lines that are negative? So when is it traveling backwards with a constant negative velocity? Never. Or at least not in this graph. So, Stephen, question number 3 is asking you about what? Okay, turning around on this graph requires that we go from where to where? Positive to negative or negative to positive, right? Because that's when that shows us the direction. So in this case, there isn't one instant when it turns around, but if we went from 200 to 275, because that's when what happens on this graph. It's at rest, but before it was at rest, which way was it traveling? Forward, and then after it's at rest, it was traveling backwards or negative, right? So on question number 3, when does it turn around? You would have to say whenever it goes from a positive to a negative, so we could say from 200 to 275, technically it's turning around.
Yellow. Hold on to that.
Yes, because on this graph it's velocity. It's moving, it's a car on cruise control, remember?
It's moving just at us from
It's moving, but at a constant rate in the yellow section. Because the y-axis remains constant, but that means that it's moving in this graph. All right, so, Rachel, let's talk about the 2 pink sections. Hold on. All right, so the last 2 sections on the graph. Well, there's 4 sections. Hey, you might want to listen to this one. This is where it gets fun. All right, there's 4 sections left on the graph. 2 of them are pink, 2 of them are green. There's a reason why I colored those, the colors that I did. Okay? Let's talk about the green sections first. So, on the first green section, from 25 seconds to 50 seconds. What's happening to the velocity during that time? That velocity is speeding up, or it is increasing. Okay? Now, let's talk about from 275 to 500. What's happening to the y values on that graph? From 275 to 500. Those values are getting bigger, but they're getting bigger in the negative direction. Remember, on velocity, the negative sign only tells you what? Direction. What's the fastest speed that this object ever reaches? 5.0 meters per second. It just so happens that 5.0 is in which direction? Backwards, or in the negative direction. Negative 5 is a faster speed than positive 3. It's just in the other direction. So on this graph, what is green? What are the green sections representing? Something going faster. The first green section is something going faster forwards. Hey, easy. The other one is faster backwards. Because, hold on, let me finish. In both cases, that graph is moving away from the x-axis. Does that make sense? And what does the x-axis represent on this graph? Rest. Well, yeah, it's time, but when it's on the x-axis, that means it's at rest. Pink means what's happening. It's slowing down. It's decreasing in speed. Even though from 500 to 600, the line is going up, but it's getting closer to what? It's getting closer to 0, and that means it's slowing down. Alright? We can review a little bit at the beginning of the period tomorrow, then quiz,
In
open
the yellow
note.
part, it's not going any farther away from